Voltage. We're going to start off with some review. Electric field. Supposing we have a big planetary charge of -2 microcoulombs sitting right there, and we're at a location, what we call a field point, somewhere out in the electric field, 75 centimeters to the right, 0.75 meters to the right. Aisha, what does A want me to find? Magnitude and direction right there. Well, there's two ways I can find electric field. I can find electric field, symbol E. Please don't confuse E, electric field, with energy. I know they both start with E, but I'll use PE for that, or KE for that. We can find it if we know the force at a location and the charge at that location, or if we know the planetary charge that's sending out the electric field in all directions, like the invisible tentacles of an octopus. I can calculate it by going K big Q over R squared. I guess technically absolute value, right? Which method am I going to use here? You know what? They gave me a distance, 0.75. They gave me an R, 0.75. I'm going to use this one. So if you want me to find the electric field, symbol capital E with a vector, it's going to be KQ over R squared. It's going to be 9 times 10 to the 9th. -2 microcoulombs or just 2 microcoulombs? We're going to use the sign to figure out the direction ourselves. All over 0.75 squared. I think this should work out evenly, actually. I think. What do you get? It's going to be 18 divided by 9, which is 2. And it's going to be 2 times 16. It's going to start with a 3-2. Yeah, I think. Yes? 32,000. Units. It's tough to get the electric field units from this version of electric field, but from this version of electric field, it's clearly something per something. Direction. Which way would a positive sitting right there want to move if it could? West. I'm going to go with left because I always botch east and west. In fact, I did that this morning, but my lefts and right I'm pretty good at because I'm a lefty. I just left. But if you said west, I'm giving you full marks. Gabe, what does B want me to find? Now, my first thought for force was, don't write this down, don't write this down. Well, maybe I could go K, Q1, Q2 over R squared. Wait. What did we find in part A? Is there a way to write electric field strength that contains force in it? You know, one of the nice things about electric field is it also provides us with a shortcut to calculate force. If we know the electric field at a location, Hannah, you tell me the charge you want to put there, I can tell you what force that charge will feel without having to go K, Q1, Q2 over R squared. Instead, I can go the force is equal to QE. Danielle, it's a 1 coulomb charge. Put your calculator away. In your head, Danielle, can you please go 1 times 32,000 in your head, please? Oh, I weep. Were you actually doing that on your calculator or something? Okay. Wow. I mean, if it was Ethan, I'd understand that, but wow. Units, now it's force. Newtons. Direction, a positive would feel the force left if they had asked for a direction. Oh, heck, we'll stick a direction on there just for giggles. And I could repeat this procedure. I could find the force on a 2 coulomb charge. In fact, it would be 64,000. I can do that in my head without a calculator. And I could even handle the 1 millicoulomb. Milli is 10 to the -3. I think it would be 32 newtons. I'm going to skip B and C, though. Or sorry, C and D. Point is, one of the nice benefits of electric field, among many other things you'll learn, is it's a great shortcut. If you happen to know the electric field and location, you can save yourself some work. For energy, for potential energy, there is something similar. So electric field tells us newtons of force per coulomb at that field point. For energy, there is an analogous, a similar concept that tells us joules of energy per coulomb at that point. And we call it potential, not to be confused with potential energy. It's just potential. Now, it's also called voltage, but you'll find more and more textbooks will call it potential. I prefer voltage because there is potential to confuse potential with potential energy. But I'm going to flip-flop between both to expose you to both terms. It's given the symbol capital V. Its units are joules per coulomb because that's the definition of a volt. A volt is defined as the potential energy per charge. That's how we defined a volt. And so its units are joules per coulomb, but this is such an important unit, we've given it a name. We call it a volt, named after Alexander Volta, who did a lot of work and built some of the first reusable, sizable batteries and things like that. Okay? We must be careful not to confuse potential with potential energy. Oh, it gets worse. Sorry, but it does. Example 2 says, fill in the proof to find the potential or voltage due to a point charge, big Q. So in the same way that we have an electric field there from this planetary charge, there is also a voltage there from this planetary charge. How can I calculate it? Well, Nick, first of all, potential energy was K, big Q, little q over R from last day, Lorenzo. And since voltage is defined as the potential energy per charge at that location, all that's going to happen is the little q is going to cancel. You'll get this. Voltage in the box here is K big Q over R. And this brings us to our significant problem. Put your pencils down, look up. Voltage, electric field, force, potential energy, potential. There is a lot of room to mix up the equations, and I have to forewarn you on a test. If I say to you, find the potential, and the question happens to have two charges, and you find the potential energy, I have to give you 0. I can't even give you any part marks. That would be like I said to you, find the force, and you found the time. Thank you for finding the time. I'm glad you did that. It's not what I asked. There is potential to mix up potential energy, force, and electric field, potentially. So the message is, don't put off doing all the homework and think, oh, I can just cram this and learn it at the last minute. But otherwise, this is my failure as a teacher, Grace. I've, for 10 years, tried to come up with a stupid way to keep all of these things straight. I got nothing except formula sheet. What I am going to say is, get in the habit of getting your formula sheet out every class for this unit. What I'm actually hoping I can do, Lorenzo, is even train your eyes to look at the right place. When your brain thinks potential, it glances in the right area. When your brain thinks potential energy, it glances in the right area. When your brain thinks electric field, it glances in the right area. I'm hoping we can build a hardwire, a little circuit there, maybe. I don't know. Second problem. What letter is that? Don't write it down. Is that a capital V or a lowercase v? You can't tell. You know what? In my writing, maybe, by the way, if it was a lowercase v, what's that mean? What physics thing is lowercase v? You all know this. Velocity or speed, okay? If it's an uppercase v, it's voltage. We are going to be running in a couple of days to an equation that has a lowercase v and an uppercase v in it. And it will be tempting for you to sloppily cancel them when they can't. So this is the trick I'm stealing from my first year physics prof. Whenever you're going to see this for the rest of this unit, in fact, for the rest of the year, anytime I'm drawing a capital V, which is potential, another word for which is potential, another word for which is, thank you. So anytime you see me write a capital V, which is potential, another word for which is, I'm going to do like a font. I'm going to put wings on it, like a serif font. That's a capital V. That's a lowercase v. And no matter how messy I draw it, that's a capital V. That's a lowercase v. Now, why did I just lose all of my image there? That wasn't very, very good. Let's see if I can bring it back, Mr. Dueck. I hope. Whew, had me worried for a second there. So I'm going to be doing that notation for the remainder of the year, okay? Example 3 is the same picture we started with in example 1. It's a -2 microcoulomb charge. We're 75 centimeters to the right. Only this time, Maggie, part A wants me to find what? The potential. Another word for which is? Okay. So I have two ways to find voltage. It's defined as the amount of energy per coulomb, joules per coulomb. But for a point charge, it was K big Q over R. Not R squared, that would be electric field. So which one am I going to use here? Again, hey, they gave me a distance. I'm probably using the one with the R in it. The potential, the voltage, is going to be K big Q over R. It's going to be 9 times 10 to the 9th. In the voltage equation on your formula sheet, did I put absolute value signs around the Q? Then voltage can be negative, can also be positive. In this case, it's going to be negative 2 times 10 to the -6 all over 0.75. So the answer is definitely going to be negative. 9 times 2 is 18, divided by 3/4. That's going to be 18 divided by 3 is 6 times 4. It's going to start with a 24. Pretty sure. 24,000, I think, yeah? Negative 24,000. Units, you could say joules per coulomb, but we have defined that as a volt. Danielle, what does B want me to find? Not potential, but potential energy, not to be confused with voltage. Now, I could do this. It says we're putting a 1 coulomb charge right there. Don't write this down. I could go, oh, potential energy is K, Q1, Q2 over R, not R squared. But wait. What did I find in part A? Is there also a version or definition of voltage that contains potential energy in it? Much like if you know the electric field, at a location, it's a nice shortcut to find a bunch of forces at that location. If you know the voltage at that location, we have a nice new version of potential energy. It's QV. You could also write VQ, but I'm trying hard to make everything look like MG from Physics 11. I'm trying to reinforce that mathematically charge, when it comes to electricity, behaves an awful lot like mass when it comes to gravity. So if you write VQ, I'm not taking marks off, but I'll go QV. Danielle, what's the charge at the location in part? What's the voltage? In your head, Danielle, without a calculator, what's 1 times negative 24,000? Which makes sense because that's how voltage is defined. It's defined as the number of joules per coulomb. Well, if you have 1 coulomb, then you'll have negative 24,000 joules. What would the answer for C be? Negative 48,000 volts. Sorry, joules. What would the answer for D be? I would put a 1 times 10 to -3. It would still start with a negative, and I think it'd be negative 24 joules. But I'm going to skip C and D. So what's voltage, Nick? It's also sent out by a charge. It's a consequence of electric field. You know what? It's the amount of energy per coulomb at a location. So, if we know the change in voltage, what's change in anything? Did you say minus? The math word for subtracting is difference, and so the change in voltage is also called the potential difference. If any of you go into electronics or become electricians, you'll always talk about a potential difference. Current will only flow if you have a potential difference. If two objects are at the same voltage, no current will flow between them. That's why birds don't die on wires when they land on the wire. They are right away brought to the same voltage as the wire, and so current will not flow through them as long as they're not grounded. If we know the change in voltage, the potential difference between 2 points, we can find the work required to move a charge between these 2 points, because if we define voltage that way, it seems reasonable for me to say the following. Once you've written that down, look up. It seems reasonable for me to say that the change in voltage is the change in potential energy per coulomb. And I think change in potential energy showed up in one of the ways that we wrote work. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. They used to love giving this kite shape on the old provincial exam. And in fact, often what they would do is they would give kids that angle, theta, and you would see kids putting a dotted line, trying to split it in half and turn it into triangles. Voltage, like energy, is a scalar, so no need for tip to tail or nothing. Who cares? They love to give really complicated looking diagrams that ended up being really, really easy. I think the very, very first thing I'm going to do is I'm going to label this Q1. I'm going to label this Q2. Although, Trevor, what do you notice about the magnitude of Q1 compared to Q2? They are the... And what do you notice about this distance from X compared to this distance from X? They are the... So I'm going to be lazy. I'm going to find the potential from Q1 and just double it. I can only do that because this is a perfectly symmetrical diagram, but because it is a perfectly symmetrical diagram, why not? So this wants me to find the voltage at X, and that's going to be 2 times the voltage from Q1. You okay with that, Trev? So that's going to be 2 times K Q1 over R1. It's going to be 2 times 9 times 10 to the 9th. Q1 positive. If it was negative, I would put a negative in here, but positive 2.5 times 10 to the negative 6. All over 0.2. I think this works out evenly. Yeah, it does. Should get something in the 100,000 range, I think. Yes? Yep. What'd you get? Units? Thankfully, a fairly easy unit to remember. Okay. So what does that mean? Well, among other things, if you put a 1 coulomb charge right there, it would have 225,000 joules of energy. But we can now do some work questions. Jacob, what does B want me to find? So we want to find the voltage or potential at location Y. That's going to be 2 times the voltage from charge 1, but at location Y. In fact, you might be able to just backspace, and I think all you need to change is the R value. It's going to be 2 times 9 times 10 to the 9th, 2.5 times 10 to the negative 6. Ooh, this won't work out evenly. 0.35. 35 is 7 times 5. We're dividing by a 7. 7 is a yucky prime number that gives you yucky repeating decimals. So give it to me all the way to the decimal point. Hannah, what'd you get? I think it starts with a 90-something thousand, I think, yes? Or no, is it 100 and something? Sorry, you're right. So 128, 571, blah, blah, blah. That's accurate enough. Okay. Chloe, what does C want me to find? The potential difference. Not the potential difference. Starting where and going to where? Oh, they told me we're going to go X minus Y. Okay. The potential difference, or the change in voltage, is going to be Vx over, Mr. Dueck, minus Vy. So it's going to be 225,000 minus 128,571. That'll be something in the 90,000s. That's what I was remembering, I think. I hope, yeah. And use your answer button if you can, because the 225,000 is easy to type. What'd you get? Sorry? 964. 28? 29? Okay. And that is still volts, because it's a change in voltage. A change in voltage, a potential difference would be voltage. Sam, what's D want me to find, Sam? Okay. I can't go force times distance, but I can go work equals change in potential plus change in kinetic. And I think it does say assume the charge starts and ends at rest. Does it not? No? We're going to assume the charge starts and ends at rest. Now, don't write this next bit down. Normally, I would say, what's changing anything? And you would say, and so I would go, okay, don't write this down. It's going to be that. And then I would say, okay, it's going to be K, Q1, Q2. Ooh. But wait a minute. What did we find in part C? I got to be fussy. We didn't just, the voltage, the change in voltage, the potential difference. And is there a version of the voltage equation, if I put a change in, that has a change? How would I get the change in potential energy by itself? In other words, and I'm done, which I'm going to suggest is way shorter than finding potential final, finding potential initial. Now, we had to walk through all of this, but if I knew the potential difference somewhere, it gives me a great shortcut for finding out how much energy is required to move a charge from one location to another. This is going to be, how big a charge are we moving, Mr. Dueck? 1.25 millicoulombs, 1.25 times 10 to the negative 3 times 96429. And Kimia, you still have that stored on your calculator. I hope all of you do. How much energy would it take? This is also nice because in terms of relative to 0 at infinity, this took care of all that for me. What'd you get? 121 joules? Anybody else? Yeah. Voltage, also called potential. Change in voltage, also called potential difference. Two ways to calculate voltage from the definition, the amount of energy per coulomb. So it's going to be potential energy divided by Q. Or if you know the planetary charge that's causing the voltage, KQ over R. Example 5 says, prove that if a charge begins and ends at rest, then the work done in moving Q is given by that. Okay. Work equals change in potential plus change in kinetic. And if we start and end at rest, that's going to be 0. What's change in anything? So this is going to be PE final minus PE initial. Except instead of writing K, Q1, Q2, I'm going to use the definition of voltage, which was the potential energy per coulomb. And I'm going to write this as QV final minus QV initial. I'm going to factor out a Q, GCF, and I'll have final minus initial. And what's final minus initial the same as? So, Sam, I was a bit sneaky. I already used this to solve the previous question because I forgot to put this derivation before the previous question. I need to put this before example 4, and then we can derive that and then use it. But it kind of, I think, is fairly obvious too. So I put it on some firm physics foundation. That's voltage. So let's summarize. We can find voltage by finding the potential energy that a test charge possesses and dividing. That's joules per coulomb. How will I know to use that method? I don't know the big planetary charge that's causing the voltage. And they didn't give me a field location in meters. We can find voltage using the point charge equation, where you have a planetary charge that's creating the voltage, and it varies depending on how far away you are. We can find the potential energy of a system if we know both charges and their separation distance. We can go K, Q1, Q2 over R, or K, big Q, little q over R. I can find the amount of energy that's stored that way. Or I can get this potential energy by itself. It's QV. I can find it if I know the voltage at a location. Then just tell me how big the charge that you're putting at that location is, and I can tell you how much energy that charge will possess. Little note, potential energy and potential are not vectors. They have no direction. So if we have several charges, add them up. No tip to tail, no trig, just add them up. Be aware, though, that some might be negative if you're dealing with negative charge. Is that okay? What's your homework? I assigned 1, 2, 3. If you look at, or is your lesson 5 exercises on a next page? Or are you already circled 1, 2, 3? Or does it start on the next page? Oh, okay. You're going to notice more and more in these diagrams, the microcoulomb is kind of getting schmooshed, and that's because these diagrams were typed in Word 1995 for Mac, and they're starting to die, and I'm trying to avoid retyping them if I can, but I'm probably going to have to. It's just hours and hours of work that I'm trying to avoid. So that there is supposed to be microcoulombs. 4, 5, 6. You can skip 7. You can skip 8. Yeah, 9. Or 9, yeah. And 12. So what did I sign, Mr. Dueck? 1, 2, 3, 4, 5, 6, 9, 12. Let's circle that on your guys' copy. Oh, I don't have the copy loaded yet. Okay.